Welcome to the day 14 of Advent of Cyber. Let's dive into the storyboard and see what's happening in the city of Wereville today. What have the elves got themselves into, and what's our job role of today? Into the story here, it says it seemed as the sun rose this morning, it had already been decided that today would be another day of chaos in Wereville. At least, that's the feeling all the folks at the DoorDasher got. DoorDasher is a Wereville's local food delivery site, a favorite of the workers in the best festival company, especially on the long days when they got home from work and just can't bring themselves to make dinner. Well, we have all been there, I'm sure. Well, on Wereville resident was feeling particularly tired this morning and so decided to order breakfast, only to find King Malhare and his banded bunny battalions had seized control of yet another festive favorite. DoorDasher had been completely rebranded as Hooperoo. All the Wereville's festive dishes had been changed as well. Reports started flooding into the DoorDasher call center, not just from the customers. The Health and Safety Food Organization was on the line too, utterly panicked. Apparently, multiple Wereville residents were choking on what turned out to be fragments of Santa's beard. Authorities were left tangled in confusion today as Hooperoo faced mounting backlashes over reports of country impersonation. Customers across region claim to have been served what appears to be authentic standards of Santa's beard in the place of traditional noodles. A spokesperson of the Health and Safety Food Bureau confirmed that several dishes required gentle untangling, and one incident involved a customer achieving accidental facial hair synchronization. Oh my god. Breaking news: the DoorDash Beardgate, customer outreach, and assault on the Italian cuisine and my immune system. That's a breaking news of today's morning headlines of the Wereville city. Immediately, one of the security engineers managed to log on and make a script that would restore DoorDasher to its original state. But just before he was able to run it, Sir Carrot Bane caught wind of his attempt and locked him out of the system. All was lost until the SOC team realized they still have access to the system via their monitoring pod, an uptime checker of the site. Your job, which means our job, as a SOC team member of DoorDasher, can you escape the container and escalate your privileges so you can finish what your team started and save the site? Okay, so today's learning objectives of us is learn how containers and Dockers work, including images, layers, and container engine. Explore Docker runtime concepts like sockets, daemon API, and common container escape or privilege escalation vectors. Apply these skills to investigate image layers, escape a container, escalate privileges, and restore the DoorDasher service. Do not order Santa's beard pasta. That's a strange thing. Okay, for today's machine, I've already turned them all on because it requires some time to boot up. And I've also opened them on a new tab. They seem to be okay. We have it here, so we can do something like this. So yeah, I have both of them powered on in a different tab. Now let's move to the next section of today's challenge and see what's there for us. What are containers? To understand what a container is, we first need to understand the problem it fixes. But plainly, modern applications can be quite complex. First thing is installation. Depending on the environment the application is being installed in, it's not uncommon to run into configuration quirks, which makes the process time consuming and frustrating, which is true. Troubleshooting. When application stops working, a lot of time can be wasted determining if it is a problem with the application itself or a problem with the environment it is running in. Conflicts. Sometimes multiple versions of an application need to be run, or perhaps multiple applications which need, for example, different version of Python to be installed. This can sometimes lead to conflicts, complicating the process even further. If reading these problems, your brain conjured up the word isolation as a solution, well, you're on to the right track. Containerization solves these problems by packing applications along with their dependencies in one isolated environment. This package is known as a container. In addition to solving all the above problems, containerization also offers further benefits. One key benefit is how lightweight they are. To understand this, we'll have to now take a big, brief look at container architecture. Containers versus VMs. To illustrate container architecture, let's examine another form of virtualization, which is virtual machines. Virtual machines, like the ones you have been booting up on this platform throughout the advent of cyber. A virtual machine runs on hypervisor, software that emulates the manages multiple operating system on one physical host. It includes full guest OS, making it heavier but fully isolated. Containers share the host OS kernel, isolating only application and their dependencies, which makes them lightweight and fast to start. Virtual machines are ideal for running multiple different operating systems or legacy applications, while containers excel at deploying scalable, portable microservices. Well, this is a good comparison between virtual machines and the VMs. Now, again, I have not read through the further, and so I don't know about it. But I would go a little tangent into explaining it a little more deeper, so that you will get an actual idea about what exactly virtual machines are, containers are, and what are the actual problems which they are solving. Because I feel containers and Dockers are the fantastic way of you deploying your any industrial based applications, or anything which would require scalability, which would require some flexibility of the applications. So I will go a little deeper into it. I'll exit out of my virtual machine and choose a pen to write here. I'm not able to select it. Okay, I hope this does right and it's also being recorded. That's fine. So, let's understand how a computer works before we get into what the problems are and what we are solving into. Now, when you look at a computer, let's say you have a machine here, and this is containing about the hardwares. Now, forgive me my handwriting, because the table is a little messy here. Okay, so this is the hardware part where your RAM, your CPU, your graphic cards, everything sits there. The basic heart or the skeletal part of a computer is sitting there, which is the hardware parts of it. Now, what we do is we have something which needs to interact with these hardwares and make it usable for us. So we have an intermediate situations like an operating system. Now there are other intermediates also into it, like the kernel, like the one which talks to the operating system as well as the hardwares. But we'll not get too much deep into it because that's a whole different concept about operating systems and everything. So generally, we have an operating system which has inbuilt systems of talking to the hardware. This is where we can have our Windows system into it, or we can have Linux, or we can have our Mac. Now, this is a understanding of a computer. Now, what happens is that when I have a application, let's say website. Now, my company runs a website. So what we initially did was we wanted to host that machine. So we got a server, let's say one piece of hardware, maybe old laptop, and we hosted the server here. Well, that's good. So we hosted with an internet service provider, so ISP here, and this was the internet there. This is a very good example of internet. Let's call this as the internet, and customers were coming into our website and then accessing whatever needs to be accessed from there. Now what happened is this was so good, so very good. If I wanted to host something, I could just update it and upload it to the server here, and that would just synchronize with the ISP and the internet was available. But what happened is that I became a little famous. So multiple users and multiple customers started coming into my network through the internet. And this server was overloaded with a lot of data which is coming through the ISP's network to the server. Server could not handle it. What we did was we replicated this. So we bought another server, let's say another machine, and hosted the same copy of the server. But this time, what we did was we also wanted to distribute these services. So we sent half of them there and half of them here, distributing the traffic of the website. That's good. But what happened? Since I was getting more and more famous, the customers started to come in more. So huge number of traffic started to come. That's the reason we came up with the same solution, which is that we bought another server, we distributed these traffic using some load balancers, and the job was done. But here's a twist. Now I wanted to do some changes to the server that, let's say we are launching a new product. So I wanted to do some changes. Now that needs to be replicated in all the three environments. Let's say this is scaled up and I had such 10 servers hosting my services. So I have to update in all of these 10 servers so that they reflect the same thing there. Is that not frustrating? I would for sure, no way on earth, I would do anything that would take my time of configuring same things to all these servers. Not just that, now since these are all independent servers, there could be some independent dependencies that each of them could have. Let's say there is one version of Apache which is running here. The Apache which is running here could have some issues with running PHP's version. So it's another conflict which I can't resolve because I want my products to be synchronized in the same way and everyone at the same time should be able to get the same product. Oh wow, Kali Linux just made our day. So that's the problem here. So this is the problem. Now I am trying to bring in multiple machines here and trying to host them. To solve this, we have containers. Now, to get into containers, it's a little complicated stuff. So let's take an example of what a virtual machine does and give you an example of trying to get a solution out of virtual machine into this and then show why containers are cooler than virtual machines. Now, if this is the general case of our server where we are taking in a hardware, installing an operating system, and then hosting our containers, that would take a lot of problem to us. So what we have? We have industry's best solution, which is use virtual machines. Now, what exactly are virtual machines, right? So we discussed that a computer has one layer called as the hardware layer. Now this is where our RAM and this is the CPU's place where it lives, and even your graphics card if you require, everything just stays here. Now this is nothing but the plain metals. These are just the bare metals, so we call them as the bare metals. Now in general cases, we would have an operating system lying there, which is that our Windows or our Linux or our Mac, or if you are crazy enough, you have dual booted to a Windows and a Linux machine. So that's depending upon you. In case of a virtual machine, there are two types of virtual machines that we can have, which is depending upon what type of hypervisor that you use. Now, what is an hypervisor? Hypervisor is nothing but a layer in between, which is, let me just write down hypervisor right here. So this is a layer between the hardware and anything that we will install here. That is, this enables us to give a virtual environment of the hardware that is there. For example, if I had 100 GB of RAM in my system, and let's say I had 100 GB of CPU processing also for my system. In a traditional computer, all these resources, all these would be given to your Windows machine alone, right? Because you're installing that on just a bare metal. So you have installed operating system on a bare metal, and all those resources are given to the Windows machine. If that's using, well and good. But if that's not using, that's being a waste of resources. So what they came up was that What if we remove this part of Windows here and create a separate layer whose job is that it's going to split up these hardware resources. Let's say I want to install a Linux machine, which just requires, let's say, 32 GB of resources of RAM and requires 2 GB of CPU processing. So it's a Linux machine which just requires these two configurations, and I have 100 of them. So I can split some part of the RAM and the CPU so that I can give this to the Linux machine that I want to host. So this is the Linux machine here. And what about the rest of the things? This can be used for giving to other machines. Let's say now I want to host a Windows machine which requires 50 GB of RAM and let's say 20 GB of the CPU processing for it. I'm just giving all hypothetical numbers. Please don't go and fact check about them. So we get for the Windows machine. Now what's happening? We are distributing the same amount of resources, which initially was being accessed by one machine alone, is now being distributed between two machines. That is Linux and the Windows. With the application which does this job of isolating the hardware resources is called as a hypervisor. So when a Linux machine is viewed from its perspective, it thinks that it's the only machine that is existing on this entire hardware. It has full control over the 32 GB and the 2 GB of the system resources. Same goes with the Windows. It thinks it's the only boss that is existing on this hardware. It thinks it has 50 GB of RAM and 20 GB of RAM, and that's entirely given to the Windows machine. That's what is happening in a virtual machine. Now, there are two types of virtual machines, as I already said. One is depending upon the type 1 and type 2 hypervisor. The one which where we have the hardware and a hypervisor just installed on top of it, and then we have our small virtual machines, let's say like the Windows, the Linux, and those things. They are all installed upon on these hardwares. Such situations is called as the type 1 hypervisor. It's where on a bare metal you install a hypervisor, and on top of that we have multiple virtual machines running. Now, another type of hypervisor is the type 2 hypervisor. That's what I feel generally all of you watching this video would be doing, because that's what even I am doing. I have a host OS. Let me clear this much part. Yeah. Now, what I have in my case is that I have the bare metal here. And on top of this, I have a Windows operating system. So OS, and that is the Windows 11. On top of this, I have installed a hypervisor. This is called as the type 2 hypervisor. Now, don't go with my handwriting. It's seriously bad because my table is messy. So, yeah. Now, on top of this Windows machine, we have a hypervisor. And inside this hypervisor, we have our Kali Linux machine. We have our Ubuntu machine. So Ubuntu Linux. So all these are hosted upon this. Now the difference between the type 1 and the type 2 is that in a type 1, the Windows operating system decides and controls the resource allocation of the hardware which is available. Now in my computer, if I say I have 32 GB of RAM, and this RAM is being used by the Windows system. If it wants, it can use the entire 32 GB of RAM. But also using a hypervisor, the small section of this RAM, let's say I've given 2 GB of RAM to my Ubuntu machine, that's going to be done by virtualizing the resources for the Ubuntu machine. That's the classic example of me using a virtual machine of Kali Linux here on my Windows 11. This is called as the type 2 hypervisor. Now, we'll not get into all these things a little in detail because we are talking about containers now. Now, what exactly is a container? For a container, we are solving another big problem with the virtual machines. Now, in case of virtual machines, if you can see here, it all depends upon the resources which is being supplied to it. For example, this machine it is an independent machine, which means that it has complete control over the specified hardware resources that is provided to it. So let's say I have a Windows machine here. Even my tab seems to be not writing properly. Uh, so yeah, let's say I have a Windows operating system here. So the Windows operating systems comes with its own dependencies, comes with its own requirements. Like it requires an operating system, it requires its own kernels to talk to the hardware resources. Because all that a hypervisor is doing is that it's allocating the hardware resources and providing a virtual resources to these Windows machines or these virtual machines. And these virtual machines come with their own kernels, which is nothing but an intermediate which communicates with the hardware and the operating system to say, yeah, this is what you can do, this is what you cannot do, and it does that job. So it comes with its own stuff. And same with the Ubuntu machine that we'll install upon any of these hypervisors. Now, the problem with these things is that they are bulkier. Now, they require a lot of resources. They also come with a lot of extra storages, which is required for storing all these machines. To come up with a solution to this, we have containers. The containers, what they do is you have a bare metal here, which is the machine that we want to be using. So we have the bare metal. On top of this, let's say we have a Linux operating system, Linux, and let me call this as I have Ubuntu. Now, instead of I installing a hypervisor and then installing an entire new operating system, I see that Ubuntu already has its own kernel, which means that it interacts with the hardware and the operating system by itself by having its own kernel. Why not I create a system which just uses the host kernel and then requires nothing else, but it can be an independent operating system by itself, and remove some of the dependencies based upon the hardware communication and anything which requires the physical aspects of a operating system is all being managed by the operating system which is already installed. With that, we get the option to scale, because if I have a suitable operating system already installed on this same like the type 2 hypervisors, we can install multiple containers inside them. They are lightweight, they can be cloned easily, they can be replicated easily, and they can be used and scaled at a larger scale compared to any virtual machines. Now, virtual machines can also be replicated, they can be cloned, they can be mimicked, and they can be used for hosting all your services. But the problem with virtual machine is that they are bulkier. They require their own resources, they require their own supports, they require their own storages. Whereas a container uses the shared resources and the shared operating system's contents from the host OS itself. It just virtualizes and replicates the application and the operating system's functions itself, which means we have a lighter version of an operating system. Now, this is the solution that we are using for hosting and scaling our services. That's where containers become a cooler thing. That's where Dockers are preferred when it comes to hosting any small and isolated environments for your applications and dependencies. Now, enough of my theory. I see the video to be going too long because we have a challenge to also finish. Let me clear my screen, get out of this, and get into the virtual machine here. I hope the VMs don't terminate themselves. So let's see. Okay, we have some sufficient amount of time, so we can continue with this here. Applications at scale. Microservers are a switch in style of application architecture, where before it was a lot more common to deploy apps in monolithic fashion, built as a single unit, a single code base, usually as a single executable. Okay, I'm sorry. I also forget a point that with containers, you can easily clone them and you can host them. So if you want to just update one particular thing, there is a master controller of a container, and you can just upload your stuff to it. It's going to break down and replicate it into a multiple step and deploy that. So while reading through this, that point came into it, so I just added that. Okay, let's continue reading here. More and more companies are choosing to break down their applications into part based on business functions. This way, if a specific part of their application receives high traffic loads, they can scale that part without having to scale the entire application. This is where the lightweight nature of container comes into play, making them incredibly easy to scale to meet increasing demands. They become the go to choice for this increasingly popular architecture. And this is why, over the last 10 years, you have started seeing the term more and more. You have been noticed a layer labeled container engine. Was my face on the way while I was showcasing that? Maybe. Um, I'm sorry for the viewers. So you may have been noticed the layer labeled container engine in the diagram. A container engine is a software that builds, runs, and manages containers by leveraging the host system's OS kernel features like the namespace and C groups. They've given also an example of it here. So this is the infrastructure, which is nothing but the hardware. Then a hypervisor, that is nothing but the application which converts or it virtualizes hardware resources and provides it to the virtual machines installed. In case of containers, we have the hardware. Then we have an operating system, which is generally the operating system that you want your containers to be hosting in. Now that we have Windows native to Linux architectures being coming into it, so we can have even Windows operating system and then Linux containers. But before, it was depending upon which operating system we had, we could use that containers. And we have container engine, which is nothing but extra layer like Docker, which provides the layer of communication between the operating system and the isolated container. And we have our containers there. One example of a container engine is Docker, which we will examine in more detail. Docker is popular container engine that uses Docker files, a simple text scripts define app environments and dependencies to build packages and run application consistently across different systems. Docker is the container engine of choice at DoorDasher, and so is what we will be interacting with our interactive lab. Docker. Docker is an open source platform for developers to build, deploy, and manage containers. Containers are executable units of software which package and manage software and components to run a service. They are pretty lightweight because they isolate the application and use the host OS kernel. Escape, attack, and sockets. Okay, now they're not getting too much deep into what exactly is to be given. So let's stick on to this and finish with the challenge. A container escape is a technique that enables code running inside a container to obtain writes or execute on the host kernel or other containers beyond its isolated environment, basically escaping. For example, creating a privileged container with access to public internet from a test container with no internet access. Now, basically, what they mean is we could have two containers, and containers are generally considered to be isolated, meaning that if we have a container, this container is technically not supposed to be communicating with any other environments which is around it, like the host OS or other containers which is present on the same network or the same host operating system's container machine. So, in theory, that's the practice. But we also have techniques where we can escape, which is to bypass the security layer which isolates the container and the operating system or any other container which is there in the same environment by using some techniques. Now, this is an example that they've given is that we are trying to escape from a container which has access to the internet to a container which doesn't have an access to any internet or networking, but just because it's in the same environment, we can access it or escape into it. Yeah, now let's continue reading. Containers use a client server setup on the host. The command line utility tools act as the client, sending requests to the container daemon, which handles the actual container management and execution. The runtime exposes an API server through the Unix socket, a runtime socket, to handle the command line interface and daemon traffic. If an attacker can communicate with the socket from inside the container, they can exploit the runtime. This is how we could create a privileged container with the internet access, as mentioned in the previous example. Let's get into the challenge itself so that we can get our hands-on experience with it and then understand in a better way. Your goal is to investigate the Docker layers and restore the defaced Hooperoo website to its original service. DoorDasher, we are going to walk through the step to beat this challenge together. Access points. Now it's time to start using the machine you booted up in the task 1. Let's check which services are running in the Docker. Run the following command: Docker ps, and you should see a few services running. So let's run here. Let's call it as Docker ps, and we see them there. Now I hope we can see them in a clear way. If I increase this there, well, that seems to be having no effect. Let me go to the full screen itself right here. Pressing enter. Is it here? Yeah, it's right here. So Docker ps, which nothing but shows the processes that are running by Docker container. And we can see multiple Docker environments to be hosted, and we can even see their configurations down here. We see there are 4 Docker containers and their name. It's always a little random name, or you can even specify a name to it. It says uptime checker, where items, the Dasher app, and deployer. So there are the 4 Docker containers there, and the image names of them: uptime checker, where times, Dasher app, and deployer. So these are the names of the Docker container, and this is the command, which is nothing but what is going to be running basically inside it. Now, usually this is not defined, but yeah, it's defined in this case. It says it is created. When was it started? 42 minutes ago. And what are the ports? So now we usually want the containers to be accessing some services outside the container itself, right? So we can host any of the ports which is present inside the container and expose it to the external operating system, which is going to host those ports for the container itself. So we are forwarding all the traffic which comes to 5003 to the port 80 of this Docker container, and anything that comes to 5002 is going to go to the port 80 of this Docker container, and so wise with the other Docker container. They are all using the TCP communication for that, and that's what is given there. Now let's start reading through this. Here it says the main service runs at the IP address 5001. So at the 5001, we have the Dasher app. It's nothing but an application which is present. Explore the web application and notice the deface system Hooperoo. We know DoorDasher is a food delivery service. Let's explore uptime checkup. Well, now what we'll do is let's copy this URL and check for the service that's there. Let's open the attacker machine here and the Firefox browser there. Let's paste this here. That did not get copied. Okay, let's copy it once again. Come back to the clipboard here. Paste that into the clipboard. Now replace that with this. Press enter. And it says Hooperoo. Welcome to Hooperoo, the Easter Bunny's delivery service. Wow, that's such a bad thing. Uh, and this told Santa's beard pasta is here. Wow, that's nice. I am able to see the Santa's. Can I scroll up? Yeah, Santa's beard pasta. Wow. Yeah, now let's run the following command to access the uptime checker container. So docker exec it uptime checker and sh. So what this does is it's going to say docker execute the. So it's going to execute it with option it, which is to interact with it with a shell. Uptime hyphen checker, and then I want an sh shell of it. So pressing enter, that should run this thing. We got the shell. So if I say who am I, it says I'm the root user, and I have entered basically into this uptime checkers Docker container, which means that I'm accessing and interacting with that Docker container itself. After logging in, check the socket access by running lsla var run docker.sock. So let's do that. So ls-la var That stopped taking my input. Okay, I got the connection back. So let's do that once again. So Docker PS, that shows the processes of what Dockers are running. And to access it, we'll say Docker exec -it. Then we say the image that we want to access, which is uptime hyphen checker. Then press sh, which is nothing that what shell we want to access. Then press enter, and we get into the shell of the Docker container that we have selected here, which is the uptime checkup. Now, if I say who am I, it says who am I? It says root. Wow, that's nice. Okay, now let's continue reading through here. It says after logging in, check the sockets by running ls la var run docker.sock. So let's run that command ls-la, which is to list everything in a linear fashion, and say var run docker.sock. Press enter. It shows this file there. Now let's continue reading and see what we have there. The Docker documentation mentions that by default, there is a setting called enhanced container isolation, which blocks containers from mounting the Docker socket to prevent malicious access to the Docker engine. In some cases, like when running test containers, they need Docker socket access. The socket provides a means to access containers through the API directly. Let's see if we can. Your output should be something like this, and we have also got the same output from the command that we run. I wonder what happens if you try to run Docker commands inside the container. By running Docker PS again, we can confirm we can perform Docker commands and interact with the API. In other words, we can perform a Docker escape attack. What can we do? Let's try with Docker PS and wow. So what's happening is that the Docker has an isolation by default. So those isolations prevent any of these Docker containers to be accessing the other machines which is present inside that Docker, or anything which is present inside that host OS. But in some cases, if the privileges are given and are used in an environment for basically checking or interacting with the Docker container itself from the container, sorry, accessing the Docker from the container. So in such cases, a privilege is given to these containers, making them use the commands which you would generally be using on a host OS for interacting with the Dockers. But those privileges are also given to this container, which is technically supposed to be isolated, but these privileges are given. Now, why they're given, they depend upon the scenarios and situations, maybe while developing or testing, or in such cases, you give them privileges of Docker commands. Here, what we are seeing is that inside the container, which is the uptime checker, we're able to run the Docker commands. Meaning, even if I'm inside a Docker container, I can execute Docker's commands, which is a thing which will lead us into escaping this Docker itself. Let's instead try to access the deployer container, which is privileged container. Run the following command. So we say docker exec it deployer bash. So it's using a bash shell. So what we are doing is from this container, we are trying to escape into another container, which is the deployer application or the deployer container. So we say docker, then exec, which means to execute, it to have an interactive shell with it, and we say which docker we need, which is deployer. Then the deployer is using a bash shell, so we say bash, click on enter, and we are inside the deployer shell there. So say who am I? It says it's deployer, which means we are inside the deployer's container. That's interesting. Now type who am I and check whether the user we are currently logged in as. Explore the container and find the flag. Okay, so we need to find a flag. So ls, we see nothing there. cd ls. Okay, we are able to see the recovery script here, which means that we can get to the former version of the flag of the application which is there, and we also see a flag.txt file. So cat flag.txt, and we get the flag there. Can I copy this? Is that possible to copy? Okay, hopefully it's copied. Can I paste it there? Okay, I can paste it there. So is there a place where we can submit? Yes, let's click on check. And did we get that? I don't know, that's loading. So till then, let's continue reading also. So now let's run the recovery script.sh file there. Let's remove this and say bash. Should we require sudo privileges? I saw the command says yes. Oh no, oh no. I by mistakenly closed that. I hope that the shell is not gone. We already got the flag. Now we need to run the script of recovery script.sh. So sudo dot slash recovery script under recovery underscore script.sh. Press enter. That's going to say the hackers have been defaced. Wow, defeated. That's good. With that run, you can see yourself by refreshing the site. As a reward, you should be able to find a flag in the same directory as the script, which you can read using cat command. We have done that. And let's go here and let me also refresh this page because there was some connectivity issue in my end that has caused the machines to go down. Okay, so that's done. Let's also start answering some of these questions. It says, what exact command is command list running Docker containers? That is Docker PS. Docker PS. Press enter. You're going too fast. Please try. Seriously, what's that? Okay, next question is, what is the file used to define the instruction for building a Docker image? That's Docker file. So Docker file. Is that right? Yes, that's the right thing. Okay, bonus question. Where is a secret code contained within the news site reporting on this? This code also happens to be the password for the deployer user. They should definitely change their password. Can you find it? Okay, before we find that, let's try to refresh this page and see what's happening. We get the DoorDasher back. Wow, that's fantastic. This is what we wanted. Okay, now let's get to the extra question and find the password. Password is what they have asked. The secret code containing within the news site. Okay, this code also happens to be the password for the deployer user. Oh, that's interesting. So it says Beardgate, the DoorDasher, and hot water over hairy meals. Okay, any secret code word? You're telling me I should read all of them? Oh, the code was deploy master 2025. Let's try that there. Deploy master 2025. And this DEPOLY, right? DPO. Let's click on check. No, that's probably my spelling errors. DPLOY. Yeah. I am bad at spellings. Okay. Yep, that's right. Like the content, we have plenty more where this came from our container vulnerabilities room. We can check that out later. So let's click on check, and yes, we have finished the room of the Docker containers, escaping the DoorDash's container environment. So yeah, that is it for today's video. Let's meet you all in the day 15 of Advent of Cyber. Till then, stay happy, stay smiling. Thank you for watching. See you on the next video. Bye bye.